Good morning, everyone, and welcome to the second lecture of the Electron-phonons interactions in VASP workshop. Our speaker today is Manuel Engel, who's one of the VASP developers and has implemented much of the Electron-phonon and phonon code. He did his PhD with Georg Kresse at the University of Vienna on electron-phonons, and his thesis work has contributed towards the electron-phonon code. Yesterday I introduced phonons in VASP, and today he's going to move from that to electron-phonon interactions, specifically the renormalized bandgap via the one-shot method and many-body perturbation theory. So, good morning, Manuel. The stage is yours.
Thanks, Chris, for the nice intro again. It will be a pleasure for me to give this first part of the electron-phonon lectures. This lecture will deal with the particular phenomenon of band structure renormalization. I will tell you what that means in a few slides. And then tomorrow's part will be about the transport, electronic transport, that will be given by my colleague Enrique. All right, so before I get into the outline of the talk, I'd like to say a few words about the importance of electron-phonon physics in general. I also like to recycle this slide because it took me some time to make it. So really, for me at least, the archetypical electron-phonon effect has always been the incandescent light bulb, where you flip a switch and then the electrons are accelerated through the tungsten filament, where they bump into the tungsten atoms of the crystal lattice, and they transfer some of their energy into the lattice in form of vibrations, in form of phonons. And that eventually heats up the filament to the point where it starts to glow and radiate heat and light. And so really this electron-phonon process of electron scattering with phonons facilitates the entire incandescent light bulb. But electron-phonon physics is much more than that. It pops up everywhere. It's completely ubiquitous in today's material science. It's important to understand the workings of the traditional superconductor, of thermal conductivity, and also to understand spectroscopy experiments. But it's also important to take into consideration electron-phonon effects when developing new technologies, such as solar cells, batteries, and all kinds of electronics. All right, so the talk itself will be a two-parter as well. So first of all, today we deal with the renormalization due to electron-phonon effects of the electronic band structure. And in today's talk, we look at renormalization using two different approaches. One is a stochastic sampling approach that I will talk about first. And then I will also talk about perturbation theory. Now, perturbation theory can also be used to access electronic transport properties, so that will be revisited tomorrow. Now, the stochastic sampling approach will deal first with the definition of bandgap renormalization. So before we get into the method, I just recap what the band structure is, about what we think of in terms of renormalization. And then I tell you how you can build random phonon modes. So just sampling from a pool of vibrational patterns and then building a statistical average of those random samples to get to your observable. We can do that either via a full Monte Carlo sampling approach, or we use a so-called one-shot method that cuts down on the computational cost substantially. And finally, I will spend a few words on temperature dependence of electron-phonon effects. All right, so let's get right into it. Most of you will be familiar with the concept of an electronic band structure, but just in case, I have a quick summary slide here that shows you the band structure, or part of the band structure of diamond, where we see the low-lying valence bands with the maximum point, the VBM, the valence band maximum, and the higher-lying conduction states with its lowest point, the conduction band minimum, the CBM. And so there's a region of space in this band structure where there is an absence of allowed energies, which we call the band gap. This difference between VBM and CBM we usually call the fundamental gap. But there's an alternative definition that is called the direct gap. In some materials, the direct gap and the fundamental gap can be different. In this case, you would also call the fundamental gap the indirect gap. And so in this case of diamond, we actually see that there's a difference. The direct gap would just be at a single K point, the difference between the maximum and minimum points of this band gap, while the fundamental gap here would be indirect, going from gamma to some point between gamma and X. Okay, why do we care? Band gaps are very important properties for certain material classes. They're important for scattering experiments, very important for solar cells. And so when you want to calculate the band gap using VASP, you first solve this Cone-Sham equation where you get the eigenvalues using DFT, and then you get the band structure, you can extract the band gap. However, that usually neglects any vibrational effects, that neglects electron-phonon scattering. And so once we add electron-phonon effects on top of this picture, what we see is that the electronic band structure changes, in some cases even substantially. So here I show a comparison between a simple DFT calculation for a particular material, so this is again diamond, and then that same DFT calculation, but also including electron-phonon effects. And you see that the band structure changes, the band gap in fact closes due to electron-phonon effects here. What I show here is an effect that happens at zero temperature. We call this a 0-point renormalization. And in general, we call this new band structure the renormalized one. And yes, in some cases, this change can be quite large. In diamond, for example, here at zero temperature, the effect is about 10% of the total band gap size. And in particular, systems with very light atoms or highly polar systems can have very large renormalizations. I will get into that aspect a little bit later. All right, so now that we know what we want to compute, there are two ways to do that I will present. The first is the stochastic sampling approach, which I will outline in the following slides. So conceptually, what we do, where we start, is a simple equilibrium structure where the ions are statically fixed at their equilibrium positions. This is your usual setup in the Born-Oppenheimer approximation, where you run VASP with a simple DFT calculation in an equilibrium structure. And as I've said, you obtain this electronic band structure by solving the Cone-Sham equations. And in order to add now the information of vibrations, what you can think of is that we take this equilibrium structure here on the left and we displace the atoms by some amount and try to sample essentially different phonon modes, different vibrational patterns in different structures. So this index I here just means we have different POSCAR files essentially where we run VASP calculations for individual different phonon displacements. And then we somehow want to average over them. We want to extract the information of the vibrations from these individual samples. And so the question really is, how do electrons now behave in a dynamic vibrational system? We want to perform DFT calculations also in these perturbed structures and then do some kind of averaging. And the question is also, what can we even compute? And so to get a little bit more specific, once we look at these displaced structures, the first question is, okay, how can we even perform statistical averages here? What do we do in order to get our band structure renormalization? And intuitively, I would say this is quite simple. We imitate nature in some way by just calculating an observable O at a particular displacement pattern, XMC, and we do a Monte Carlo sampling over that. So we have many of these displacements, and we sum over all the individual contributions and generate a statistical average. We can also do this in principle at a finite temperature T. So all of these displacements could be made for phonon branches that are typical for a particular temperature. And then your operator will also, at the end, depend on temperature. So what we can do is perform DFT calculations for each of these individual steps and then simply average over them as shown here. The way I think why this is intuitive is because in nature, when you think about quantum mechanics, something very similar happens. You have probabilities, and in the end, the canonical classical path you get is essentially just the expectation value. All right, so this approach is hopefully conceptually quite simple, and it also allows us to use all kinds of higher level methods. So first of all, this includes all electron-phonon effects at higher order, because there's no mention here of perturbation theory or some cutoff or approximation. We really just run DFT calculations in displaced structures and average over them. And what that also means is that you can use all kinds of higher level functionals. So you can use meta GGA or hybrid functionals, but you could even use the band structure that you get from a GW calculation. So adding electron hole interactions on top of everything. And last but not least, you can also go beyond the harmonic approximation with this method, because you are free to choose the kind of displacements you want to make, and you can incorporate lattice effects, etc., etc. In that regard, it is quite powerful. So one last question here that we can ask is, how do we actually get to those displacement patterns? I always talk now about a phonon displacement pattern, but what does that actually look like? What is the displaced structure? And so if we write our displaced structure here, this XMC, as the equilibrium positions plus some small displacement delta tau, we can choose delta tau as essentially picking from various different phonon eigenmodes that we obtain from, let's say, a finite difference calculation. So we compute our phonon spectrum, our phonon eigenmodes. So this is, from those who remember from yesterday's lecture, this is actually just the phonon eigenvectors from the supercell or from your simulation cell. And you build a linear combination of those eigenvectors, and you pick statistical samples from this based on the probability distribution of a harmonic oscillator. So this n of t here is just a random variable with a temperature dependence that corresponds to a harmonic oscillator. And then this whole thing is mass scaled. And with this, you have a recipe for generating displacements. You simply run your VASP calculations in these cells, and then you average. Practically, how does this look like? How do we start such a calculation with VASP? Well, first of all, you start already in an equilibrium structure, and then you generate the cells. So in order to do that, the first tag you set is phone LMC equals to true. This activates the Monte Carlo sampling. In addition, you also want to activate iBrine equals 6. This is the finite difference driver that gives you your phonons. So you calculate the phonons in order to get these displacement patterns. And then you need to specify how many samples you want from this phonon space, essentially. And in this case, it's 30 samples. So you will get 30 different POSCAR files. And you can also specify a temperature at which this distribution is created. The output will look like this. There will be a POSCAR.t where you have the temperature that you specify and then a number for what kind of sample this is. You run VASP for all of these different POSCARs, and then in order to evaluate the change in the band structure due to the atomic motion, you compare your equilibrium structure, where you know already the solution of the Kohn-Sham equations and you have a gap, against the averaged value over all the displaced structures. So each of these displaced structures will give you a certain band structure that deviates slightly from the equilibrium, and it will have a difference in the band gap. And by averaging over all of them, you will get an effective band gap that is now Monte Carlo sampled. And you take the difference between the two, which will be your electron-phonon renormalization of the electronic band gap. And once again, this exists also at zero temperature. So there is a ZPR effect also in this method. Okay, so far so good. You can do that. How do you make sure that your sample count is large enough? How do you converge this kind of calculation? One way is to just keep increasing the number of samples and see how your calculations behave. And you see here on the left side on this plot that we did exactly this for various different supercell sizes. And you see as the number of samples increases, the error goes down systematically. So the more samples you have, the better your result will be. This is really typical of Monte Carlo simulations. But you see something else here, and that is with a larger supercell size, the error is already lower. So the question that presents itself here is, what if we keep increasing the supercell size instead of the number of samples? Can we also get a reasonable result then? And yes, it seems that it is possible. And in fact, the most interesting question then is, can we get away with just one sample? And this is what really the idea of a one-shot method is in this context, is that you just have one single sample with a very specifically chosen phonon mode, and you use a very large supercell for that. And so we want to replace our full Monte Carlo sampling with just a simple structure that has a very specially chosen displacement. We call this particular displacement the Zacharias-Giustino configuration. You can read up in the paper how that is exactly done. But in essence, the idea is to once again make a linear combination of phonon modes where we have this additional factor here that gives you a temperature distribution, and also we alternate the sign with -1 and 1 with each changing branch of your phonon spectrum. And then you will end up with a particular configuration that you can use to sample effectively your vibrational properties of the material. And with this single one configuration and a large enough supercell, you will get really good results as well. I will show just in a second some results we obtained with this method. And from an input point of view, from a practical perspective, now we have an equilibrium structure that we want to just get one displaced structure from. And once again, there are some INCAR tags that accomplish this for you. You set phone LMC equals true the same way as you did before with the Monte Carlo sampling, as well as ibrine equals 6 to get your phonons from finite differences. But then the difference is to set phone nstruct equal to 0. It's a special meaning, essentially, that means here I want to use the one-shot method. And in addition, in this case, we can even conveniently specify multiple temperatures. So in this case, we choose 4 different temperatures, 0, 100, 200, and 300 Kelvin. And it will generate POSCAR files with the following format: poscar.t equals then the temperature. And the upshot of this entire process here, of this one-shot method, is that it is usually much cheaper than doing a full Monte Carlo sampling, while still retaining really good accuracy. So usually the error is within a few milli-electron volts. And also it's convenient to specify temperatures like this. You don't have to deal with multiple directories. There's no need to do any additional averaging here. So if you can, this is usually a good idea. All right, I promised some results earlier. Here are ZPR results of the indirect gap of diamond that we obtained quite a while ago by now, 2018, if this is correct. And we show here the band structure calculated on the PPE level, but also on the level of G0, W0, that is the non-iterative flavor of the GW approximation. And we compare them against, so we compare first of all between one-shot method and the full Monte Carlo, where we have results that are very close to each other, but we also compare against experimental values. And They agree quite well. So these results are already very competitive at the level of a 5 by 5 by 5 supercell. Here, the 666 cell would have been too expensive at the time to calculate with with G0W0. But in principle, you can still increase the supercell size and see if you see anything substantial here. My guess is that you do not, following the results that the PBE shows. All right. Another thing you can look at is the temperature dependence, since now you can choose different temperatures to pick from your phonon spectrum. You're able to produce a plot such as this, where you look at the indirect band gap as a function of the temperature, because this renormalization will change as the temperature increases, as the phonons are more and more occupied. And here we present values from PBE as well as G0W0 and compare against literature results from LDA. Now I have to say here also that these initial values here are shifted to the same point. So they have the same starting value. So what we're interested here is really the shape, the curvature of this curve. And we compare them against experimental values. And what's evident here is that while the shape is generally the same, we do not yet get quite the exact curvature here. We don't lie on top of the experimental values. And that is in large part because of volume effects. As you keep increasing the temperature, the volume of your cell also changes, which is something that is not a priori included in this one-shot method. When you just specify temperatures, it always uses the lattice constant of your equilibrium structure at zero temperature. But what's beautiful is that if you put in the work, you can even go beyond this harmonic approximation of just having these displacements around the equilibrium, and you can include volume effects via a quasi-harmonic approximation. And once you do that, you land pretty much exactly on the experimental values. So this is something this method offers you in particular, can be very powerful if this is what you're studying. And so that leads me to my first summary of this stochastic approach, which is that we can include electron-phonon interactions to renormalize the electronic energies, in particular the band gap. These effects also occur at zero temperature, not just at finite temperature. We can achieve all of this in this framework by a statistical average over various sampled photon modes. Or alternatively, we can do a one-shot method where we use a special displacement in a larger supercell, which is usually much cheaper than doing a full Monte Carlo sampling. And we can even describe temperature dependence and can get quite close to experiments. So the advantages of this method is that it works out of the box with any density functional, even the GW approximation in this case, since what we care about are really just the electronic energies. It includes automatically higher order electron-phonon effects. What that means in detail, it will be clear in the coming slides when I introduce perturbation theory. And it can go beyond the harmonic approximation. So very powerful stuff here. But it has disadvantages. First and foremost, I think, is that this method is limited in scope to only very particular observables that you can calculate. So there's no direct access to electronic transport properties, for example, like the conductivity. Also no access to superconducting properties, no critical temperatures there. It's also really difficult to converge polar materials properly using this method. So if you have a material like lithium fluoride, for example, which is extremely polar, a salt crystal, then you will have to go to extremely large supercells in order to capture all the long-range electrostatics behavior. And intrinsically, these methods tend to be quite noisy due to how they work. All right, but that's why we have an alternative approach, one that is based on perturbation theory, which also allows us to extract the electron-phonon renormalization of the band structure. It can do more than that, but as I've said, this lecture will focus primarily or solely on the renormalization. And in many aspects, this perturbation theory approach is complementary to the stochastic sampling approach. Now, in the coming slides, I will tell you how we can get the energy change from a simple Taylor expansion of the total energy, including all the vibrational effects. I then introduce the concept of the electron self-energy. Then I will introduce the electron-phonon matrix elements that are extremely important ingredients in this approach. I will tell you how to compute these matrix elements using a supercell-based approach in VASP, what kind of workflows we offer, and finally I get into electrostatics again. So going to do electron-phonon physics in polar materials in a very similar vein that I did yesterday for phonons. All right, let's not waste time here. Here is a Taylor expansion of the total energy. So this is, sorry, not the total energy, it's the energy of a single particle that is fully renormalized by all electron-phonon effects. And this expansion as zero order term, just the cone sham eigenvalues that you get from a static DFT calculation in the ground state. So these are your typical DFT bands. And then you have contributions from first order, from second order, and also higher order in the atomic motion. So this is atomic displacements or phonons. Now here we neglect all the higher order terms. So everything that's third order or higher, we neglect. So we are here fully in the harmonic approximation. And this is exactly what I was talking about before, is that we here in the perturbative approach neglect these higher order terms, while in the stochastic sampling approach before, those were implicitly included. We do neglect also the first order term, which is this forces term. Since in equilibrium, this term usually vanishes. And at second order, we have two contributions. We have two diagrams here, Feynman diagrams that contribute. For those who are unfamiliar with Feynman diagrams, I will go over them very, very quickly in an intuitive manner in the next slide. But just so it is made clear, we call these types of diagrams self-energy diagrams, because the initial state here of the incoming electron is also the final state here of the outgoing electron. And these two diagrams, we call them Van Migdal and Debye-Waller self-energies. The Van Migdal term here is in general a complex valued quantity. We get our energy change from just the real part, and it has two first order vertices. Now vertices, I mean interaction points with phonons. So you can think of this as an electron that just travels along, it propagates in time until it spontaneously emits a phonon with a particular frequency omega, which also the scattering process, it changes the momentum of your electron into an intermediate state. So it now travels with an energy epsilon mk plus q, so it scatters somewhere. And then the phonon is reabsorbed at a later time, once again an interaction point, and you get back to your initial state with epsilon nk. And this diagram, it changes effectively the energy of your traveling electron by including electron-phonon scattering processes. And this same exact process happens here at second order with the Debye-Waller self-energy, which is now a purely real quantity. And this interaction point here is a second order vertex, meaning that the interaction here is of second order. So in principle, it's equivalent to a second derivative in the atomic energies. All right, quick disclaimer here. What is being discussed here is a simplified view. There is much more behind this. All of this comes from a very rigorous framework of many-body perturbation theory. I simply show here a Taylor expansion or Rayleigh-Schrödinger perturbation theory, if you will. The expressions I show here are given in the so-called Allen-Heine-Cardona theory, but there are more general expressions. There are also adiabatic and non-adiabatic expressions. So if you're interested in all of this, we do have some more theory now on the VASP wiki, but all of this is also available in textbooks. And then also in this AHC theory that we have implemented, this Debye-Waller term is approximated using the so-called rigid ion approximation, which replaces this potentially troublesome second order vertex with just two first-order vertices. So it becomes a diagram that mathematically looks more similar to this von Migdal self-energy up above. Okay, so let's look in a bit more detail at this first von Migdal diagram, what it looks like mathematically. And I tried to color code here the different contributions from all these pieces of the Feynman diagram as their mathematical equivalents here. So the first thing you notice is that the electronic energies as well as the phonon frequency all appear here in the denominator of this expression. These are, of course, all quantities that we can compute. We know how to compute, and VASP already does this routinely. And then there's also here a term that corresponds to the phonon occupations, which is really just a Bose-Einstein distribution. So this is a temperature-dependent term that just gives you the phonon occupation as you increase the temperature. And then the most important, interesting term here is the so-called electron-phonon matrix element, G, which stands for the interaction point between the electrons and the phonons. And this is a quantity that we had to implement. And there's quite some technical challenges that come with that. But once you have this matrix element, what remains is to sum over all this. So you have to integrate over all the intermediate states, over all the possible scattering processes. So you sum over intermediate band index M and also over all possible phonon momenta Q. And then the real part of this expression gives you the change in energy. Plus, of course, you also need the Debye-Waller contribution. So only the sum of both diagrams will give you what you want. And this is a non-adiabatic version of this diagram, which you can see here. There's a phonon frequency in the denominator. Effectively, that means you include also the energy transfer between the electronic and the phononic subsystems. If you neglect this, it would be an adiabatic expression. All right, so maybe one thing I didn't cover here is the small imaginary shift. This is a remnant from many-body perturbation theory, where it actually originates from the electron-Green's function, and it has to do with time ordering. But here we consider it let's say, a computational parameter. It gives you a small finite smearing of this expression that you can use to get a more stable real or imaginary part. And finally, the imaginary part of this quantity will play a huge role in tomorrow's lecture because it will be related to the finite lifetime of your electrons once you activate electron-phonon physics. But it's not relevant for our purposes. We are only interested in the real part. Okay, so I mentioned this electron-phonon matrix element, and it is an important ingredient. Once again, here I have a physical interpretation where you have an incoming electron that goes into a scattering process with a certain energy epsilon and k. So this corresponds here to the ket state. It scatters by either emitting or absorbing a phonon with a particular frequency omega. So this corresponds to the change of your electronic Hamiltonian due to a phonon vibration. And then it scatters into a final electronic state, epsilon mk plus q, which is here the bra state, the outgoing state. And this matrix element is exactly how you would want to compute it. You have your Bloch states, initial and final, and you have the change of your Hamiltonian, or it will often just be the change of your cone-sham potential. And this change due to a phonon mode, so we define this displacement operator here, delta nu q, it is just written as a linear combination of individual atomic displacements modulated with some phase and the phonon eigenvectors. So this is really just taking individual atomic displacements and then molding them into the phonon displacement patterns that we already know from our phonon calculations. And this opens the door, this derivative with respect to atomic displacements opens the door to do finite differences. Because what this here means is really we do a displacement of an atom kappa in a particular cell L in the Cartesian direction alpha. So this really screams finite difference. And this is what we do in VASP. We start in a supercell where you have the replica of a particular primitive cell here illustrated as these red squares. And in one of those replicas, we take an atom and we displace it by a small amount. And then we compute the change of our Hamiltonian by this atomic displacement in real space. So effectively, what that means is we take the derivative of our cone-sham potential in real space when we displace an atom. And this quantity here, we usually refer to as the electron-phonon potential. And in this case, it is given in the supercell, in this entire cell. When you look into the technical details, it is a bit more tricky than that because we have to deal with additional terms in VASP. But conceptually, this is really all there is to it. The change of your cone-sham potential when you move an ion. All right, but what we want at the end is not a supercell electron-phonon potential. We want to get the matrix elements that I just showed you. And so we need to close this change of the potential between Bloch states that originate in the unit cell, in a primitive cell, in a phonon displacement description. So we have to go from our atomic displacement to a phonon displacement. On the previous slide, I showed you exactly the equation that you can use. And we also need to transfer from the supercell somehow to this primitive cell. If we can do that, then it's just as simple as taking the Bloch orbitals here and closing this perturbed potential between those orbitals to get our matrix elements. And in order to do this transfer, we employ a simple Fourier interpolation of the potential. I say simple because maybe conceptually it's simple, but really there is a lot of technicalities that goes into this process. But yeah, conceptually it's quite straightforward. You take this, you have it in real space for individual atoms in a supercell, and you Fourier interpolate, just like yesterday with phonons, to the unit cell in the phonon displacement basis. And this interpolation procedure is pretty fast. It gives you quite a substantial speed up over a direct computation of such a quantity. But at the same time, it is quite accurate and robust. For those of you who are familiar with Wannier interpolation, I will get to that towards the end. This does not use any Wannier orbitals. There's no local basis involved. So this really just does a Fourier interpolation of this potential. All right, so with this method, we have everything. We have the self-energy expression initially with the two contributions from Van Migdal and de Beiwaller. We have the electron-phonon matrix elements, and we have a procedure to compute them. And with all this, we like to offer two workflows that you can use to obtain the renormalization at the end of the day. And the first workflow is one that is completely implemented inside of VASP. So this, what I call here VASP only workflow, where you start in a supercell and you run your finite difference calculation to get the electron-phonon potential. And that information is then written to a binary HDF5 file that can then be used in a subsequent unit cell calculation to do your electron-phonon physics. So in principle, you have to do these two VASP calculations. At minimum now, this entire workflow is a two-step procedure. But in addition to this workflow, we also offer the possibility to split your finite difference calculation into individual calculations using a Python tool that is called Felel. It's developed by the same person that develops PhonoPy. It's Atsushi Togo here in the corner. You can scan this QR code to get directly to the GitHub page. It's a freely available tool that you can use. And for those who are already familiar with PhonoPy, it works in a very similar vein. So each displacement in the supercell will be its own single VASP calculation that offers some advantages. For example, it gives you a little bit more flexibility and control over the displacements, and it can also make it easier for you to parallelize your calculation. On some clusters, running a single long calculation can be problematic, and here you have the option to split. And after that, you combine all these calculations and you get to the same point that you got with the first workflow. The information is once again written to this binary HDF5 file on disk, and you can start your electron-phonon calculation in the primitive cell. All right, with that, I would like to touch on a rather technical point. So these next few slides will be very technical, but I think it's an issue that can be very confusing when you first start these electron-phonon calculations. It is something that we are working on actively to minimize the confusion, but since it's part of the workflow currently, I felt the need to make those slides. And the issue is really with the FFT grids that we have in these various different calculations. You see, the problem is that we want to evaluate an inner product of two different things. One is the Bloch orbitals that we have in the unit cell. So these psi functions that we take in real space. So here these psi orbitals are taken as real space wave functions, if you will. And then we have the electron-phonon potential that is also given in real space. But in order for this kind of expression to work, we need both of those quantities to be at exactly the same grid points Ri. Otherwise, there will be no match and there's no way to evaluate something like this. But that poses a problem because the psi orbitals, the Bloch orbitals, come from the primitive cell, which has a real space grid that is the FFT grid of the Kohn-Sham orbitals. So that is what is given by ngx, ngy, and ngz in the unit cell in your VASP calculation. So if you, for example, look in the INCAR file, it will tell you exactly what that is. But the electron-phonon potential comes from a supercell, so entirely different cell geometry, with the Ri points on the fine FFT grid that corresponds to the Kohn-Sham potential. So this is given by ngxf, ngyf, and ngzf. And so we have a potential mismatch here between, first of all, primitive cell and supercell, since those things come from different kinds of calculations, but also in the types of FFT mesh that are used. One is the regular FFT mesh for the orbitals, and the other is a fine FFT mesh for the potential. So we need to find a matching procedure to go from one grid to the other. And I try to show this here graphically, where on the left side I show the supercell fine grid, here illustrated as points that are maybe not even perfectly aligned here with the axes because it's some kind of non-diagonal supercell or something. And I call this the RSC for supercell and F for fine. And then on the right side, I have the primitive cell with the coarse grid. So that's the grid where the wave functions live. And this is given by an RPC for primitive cell. And in order to get from the left grid to the right grid, we introduce an intermediate grid. I call this here the supercell partitioned coarse grid. What I mean by that is that I try to build an FFT grid here in the supercell that essentially looks like the primitive cell grid, but replicated. So each of these individual red squares here is just a primitive unit cell, and it has the same grid layout as the unit cell. So once we have this, it is quite easy to go to the primitive cell because all we have to do is just partition the supercell into its primitive cells and then map one to one. And here I just use the index C to indicate that this is coarse. All right. And the only tricky technical part here is to go from our initial, maybe very complicated fine supercell grid to this nicely arranged partitioned coarse grid. And we do that via yet another Fourier interpolation. So we Fourier interpolate all these fine grid points to a coarser grid that is nicely aligned with this primitive cell. Okay, and finally, yeah, we transfer these grids, as I mentioned, mapping one-to-one, and this is really finally what is stored in the HDF5 file that you read at the start of your electron-phonon calculation. Okay, so we have these three grids, and we can control these grids in various ways. So the first and most obvious ones are, of course, just the EN-cut and PREC and NGX, NGY, NGZ parameters that we can pick in either of those calculations. So of course, if you change your electronic cutoff energy, it influences the FFT meshes. A higher electronic cutoff means a denser mesh. The PREC tag also increases your FFT mesh density. I always recommend people to use prac equals accurate in these kinds of calculations. And then if you wanted to, you can also manually specify ngx, ngy, and ngz here. And in the end, we want to match this onto this. And so this intermediate grid also has a tag that allows you to set exactly what this ngx, ngy, and ngz ought to be. Because remember, this is a separate calculation. It's a unit cell calculation that you have to run at the end of all the supercell stuff. So what is set here in elf-pot FFT mesh needs to be exactly what you use as ngx, ngy, ngz, or what's reported in the INCAR. Okay, so this is all very, very complicated stuff. I hope that at least some of you were able to follow me. But the good news is none of this is relevant if you just use consistent settings between supercell and primitive cell. So if you use the same INCAR and the same prec, then VASP chooses all these values internally such that they match perfectly on top of one another. So that's quite nice. It's an incentive for you to also keep the same computational parameters between one calculation and the next. But for those of you who are power users maybe, or who like to experiment with INCAR, or maybe your supercell calculation is too expensive and you want to tweak a little bit, you can set these FFT grids manually using these tags. But also we are working on a solution that doesn't require this explicit grid matching in the first place. So stay tuned for the future. We hope we can make it much more user-friendly going down the road. All right, for a practical example of an INCAR file, how do you do these calculations? The first step is the supercell calculation, and here it's really just two tags you have to set at minimum, and that is finite differences. So once again, we have something that we run with iBrine equals 6, and we want to compute the electron-phonon potential, which you get by doing elf-pot generate equals true. And that performs finite differences to compute this change of the potential. It writes it to the HDF5 files, it is fel L params here. And in addition, it also generates for you files that you can use for your convenience. So it will generate a contcar_elf file, which will contain the primitive cell structure that you should use in your next step in the primitive cell electron-phonon calculation. And so what you can do is you just move this file or copy it over to the postcar file in a separate directory where you run the primitive cell calculation. And in addition, it writes out useful information. So it tells you it generates the fel L params HDF5 that you have to copy over to your unit cell calculation. It tells you if no primitive cell was provided by the user. So there is a tag where you can specify explicitly, oh, I want to use this particular primitive cell. Then it would tell you. Otherwise, it just uses the one that VASP finds by symmetry, which is quite nice. And then it tells you if you have used this tag before from the previous slide that specifies the FFT mesh. If you didn't do that, it tells you what it uses for the FFT mesh. And the 16, 16, 16 is what you should use in your unit cell calculation. So this should be equivalent to ngx, ngy, and ngz. And it will be by default if you keep your INCAR and your prec the same. All right. The second step, that is where all the electron-phonon physics happens, because up until this point with the supercell, we have just generated a derivative of a potential. There's not much electron-phonon physics happening. So here, that's what we want to run. And for band structure renormalization, there is a simple tag that you can set, a convenience tag, let's say, that's called elf mode. You can set this equal to renorm. And then it will set all these tags here below it to some reasonable defaults. And I think it sets some other tags as well. You can look that up at the wiki if you're interested. But this essentially are very reasonable defaults to perform band gap renormalization. So let's go over them really quickly. You have elf run equals true, which means just run electron-phonon calculations. You then activate both the Van Migdal and the Debye-Waller terms because both of them contribute to the real part of the self-energy, so to the renormalization. You want to evaluate the self-energy at the gaps. So gaps here is plural because it computes both the direct and the indirect gap if it exists. And it also sets elf n bands equals to -2. So here you usually specify how many intermediate states you want to sum over. And with -2, you just say, oh, just use all the bands that we have available in our calculation. And you will see why that is important in a second. And finally, it sets this I delta parameter, so that's the small imaginary shift, if you remember, to a small value. That is usually a good starting point. But that is something that in principle you have to also check and make sure that it gives you reasonable results. Okay, of course you can set all of these things manually, so just putting this is fine as a starting guess, but then maybe you want to change this delta parameter, you can just set elf mode equals renorm, and in addition specify this delta tag manually, and it will override it. And then you can specify a list of temperatures. So here it's 0, 100, 200, 300, and 400 Kelvin. And VASP will run your self-energy calculation for all of these temperatures very efficiently without having to recalculate matrix elements, and it will give you an output for each temperature at the end of your run. Okay, a few words to convergence and to some of these things. So when you look at the self-energy expression here for this von Migdal self-energy, I mentioned quickly that you have to sum over all the intermediate states M, and you have to integrate over all the intermediate phonon momenta Q. So these are two kinds of things where you have to converge your calculation properly. So for the Q point convergence, so it's these states essentially that you summed over, right? But for the Q point convergence, you can specify the Q points at a particular grid, let's say. So this graph here shows the convergence of the 0-point renormalization of the band gap as a function of this Q point density. Essentially, as you increase your Q point density, you go to the left of this graph and you will get closer and closer to your actual ZPR value. And if you go to infinity, it would really approach the axis and you would get the accurate result for an infinitely dense Q-point mesh. Now, hopefully you're able to see here that as you approach this axis, you will get into a regime where the points behave linearly. So if you increase the Q points even further, you will not deviate from this line and you can extrapolate the results. That's something you can do. Once you notice, okay, this looks linear, you can extrapolate towards infinity and then get your final ZPR result, your final renormalization value. But you have to do this diligently. And usually the values where you will converge for the materials that I myself tested are somewhere between 32 or 64. I rarely ever had to go beyond 64 by 64 by 64 Q points, but it is very material dependent. So make sure that whatever unit cell you have, with whatever material you have to have the right K points or Q point densities. All right, and then the other term you have to converge is the sum over states. And this is unfortunately quite tricky. You see here that the convergence behavior as you increase the number of states that you sum over is extremely erratic. There is no real system to it until you get to a regime where the difference just gets very, very small, and at some point it becomes converged. And this here on the bottom of the axis is the number of intermediate states. So you see, you really need a lot of bands, a lot of intermediate bands to converge these kind of calculations. So in this case, I would say that with 500 bands, you're well converged. And that is why on the previous slide, the default is to set elf n bands to -2. So it just uses all the bands available in order to increase the chances that this converges. If it doesn't converge and you look at this kind of behavior and you still see wiggles at the end, then what you have to do essentially is to redo the calculation with a higher EN cut, so higher electronic cutoff energy, so you can generate more bands. But with a meaningful default EN cut, so a bit higher, usually this already converges with the pseudo potentials that we provide with VASP. All right. In practice, the way to control these kinds of convergences or to test these kind of convergence behaviors is one, using a special k-points file to specify the q-point mesh. So this is called a k-points_elf file. In this file, you specify what kind of q-point mesh you want. This is very similar to, let's say, the q-points file that I mentioned yesterday, but this is for electron-phonon physics. And so you run a self-energy calculation with a particular k-points file, and then you increase the number of k-points and you do it again. And you increase again and you do it again, and then you get this kind of plot that I showed before. And the other thing with the intermediate states is that you can set the number of maximum bands to include with ELF-n bands. So you can set this, for example, to 200, run a self-energy calculation, you set it to 300, run another calculation, and then you get data points along this graph. But VASP offers you a more convenient way to test this by setting the so-called ELF-n bands sum tag, where you can specify individual points of this ELF-n band sum, and it will calculate in one single calculation all the different self-energies that you would get from these maximum number of bands. And then you can do a plot like this already from one single VASP calculation, and it's very efficient because it skips the calculation of additional matrix elements. In general, I would advise to just leave LN bands always equals to -2, and you can check with this if you are converged or not. Okay, so a quick recap of what the input and output now looks like, because all of this was scattered across multiple slides. You have your k-points as usual, you have your potcar as usual, and you have your INCAR with your electron-phonon tags in it. So that would be, in the simplest case, just elf mode equals renorm. Then you have a k-points elf file, which contains the q-points of the intermediate states. You have the fellow params HDF5 that you generated from the supercell. And finally, you have a postcar for the unit cell, which I remind you, you can set where you can copy or move the contcar_elf to get this postcar. All right, and then the output that you get from such a calculation looks like this. At the very top, it will tell you that this is an electron self-energy. In fact, there is this so-called accumulator here with an index n equals 1. If you run, let's say, this ELF-n bands sum, it will generate one such data output, one such, we call them accumulators, for each one of those values. So you would have an n equals 1 for 50, and then you would have an n equals 2 for 100, and so on and so on. So there will be multiple blocks like this. And then it reports the direct gap as well as the fundamental gap. In this case, it is another diamond calculation where the fundamental gap and the direct gap are not the same. So in this case, you see that the cone sham gap we get here from DFT without electron-phonon is different between fundamental and direct gap. The fundamental gap is smaller, of course. And also at different temperatures, the cone sham DFT gap does not change because there is no electron-phonon effects. There are no phononic effects that could scale with temperature. But once we activate electron-phonon effects, this so-called quasi-particle gap, the renormalized gap, it does depend on temperature. And you see here as the size of the gap decreases with increasing energy, with increasing temperature. So this follows the same pattern that we saw earlier in the plot with the temperature dependence. Increasing the temperature closes the gap. It's not always the case, but it is a thing that I've seen many, many times before. And then also it gives you just a difference of the two values, which is the actual renormalization. So that's at 0 temperature, this is exactly the value of the ZPRs. For the direct gap, that would be 390 millielectron volts. Okay, one final thing that I want to mention here is the problem of converging these calculations in polar materials. If you have attended yesterday's lecture, it's exactly the same. It's exactly the same correction scheme where you start with a calculation or polar materials where you have very long range interactions due to the effects of the displacement of the individual charged ions. And these long-range effects, they mean at first glance that you have to go to really, really large supercell sizes. But of course, that's very expensive. We don't want to do that. So instead of going to really, really large supercells, we employ a correction scheme that subtracts these long-range contributions due to dipole interactions. So we can interpolate the short-range part, and then we add back up the long-range contributions at the end to get the correct behavior. And if you do not do this, your physics will be quite wrong. So here I show the example of lithium fluoride, a really, really, really highly polar material. If you do not account for these long-range corrections and you have a moderately sized supercell, then you will see that your matrix elements here will go towards zero as you approach the gamma point. So that's the long wavelength limit where these polar effects are the strongest. However, if you activate this long-range correction behavior, the behavior is quite different. In fact, you diverge as you go to the gamma point. This divergence is something that you have to expect in this kind of physics. There's the so-called Fröhlich interaction that describes this very rigorously. But yeah, as you can see, the physics here will be completely wrong if you do not include the correct correction for polar materials. In order to activate this correction scheme, once again, like in the case for phonons, you want to compute first the Born effective charges and the dielectric tensor. You can do this, for example, using L epsilon equals true. And then you supply them with the same exact tags as you used for phonons, namely phone Born charges and phone dielectric. And they are included already in the supercell calculation and written to the Fel params HDF5. If they are included in this binary file, then VASP will automatically use them. However, you have control over whether or not you want to add those corrections or not. So there are tags here, ELF-LR and IFC-LR, that you can use to activate or deactivate this behavior manually. Okay, and finally, here are some results that just show that our code can produce these ZPR values for various kinds of materials, also some of which are very highly polar. So for example, here I pick out again lithium fluoride, which has an enormous ZPR of over 1 electron volt. And a vast majority of that contribution comes from the polar interactions with dipoles. So I think if you were to remove them, you would end up with something like 400 millielectron volts. That's just pulled from my memory now. Don't quote me on that, but they are a substantial contribution. But yeah, even something like magnesium oxide, for example, can pull a ZPR of about 500 millielectron volts. So that is very substantial. In this publication, we compared our results here, which is the first column, with reference results that were obtained with UBinit, different code that performs electron-phonon physics. Okay, and that brings me to the summary of the second part that deals with the renormalization using our new perturbative code. I showed you what the renormalization is in terms of self-energy diagrams and how you can obtain it as the real part of both the von Migdal and the Debye-Waller self-energies. I showed you how the entire procedure consists of two steps. One, you produce electron-phonon potential from the supercell, and then you use that supercell potential, that electron-phonon potential in the primitive cell to produce electron-phonon couplings, so electron-phonon matrix elements, and then the band structure renormalization. I gave you two important cases where you have to check convergence, namely with respect to Q points and with respect to the number of intermediate states, as well as how to treat long-range electrostatic interactions in polar materials. And finally, I want to give one more plug to this Fel tool that is available on GitHub. It does come with its own command line tool that will provide you basically a walkthrough of your calculation that keeps things consistent is called the valve, and it will give you a step-by-step tutorial essentially of how to run these calculations. Okay, so I gave this presentation already at some point where I had some words on transport, but since transport will be its own topic tomorrow, I decided I will instead give you a little sneak peek into the future of Electron-phonon, and I will talk about a feature that will be released very soon, a feature that I have worked on myself quite a bit, and that is Wannier interpolation with Electron-phonon physics. So this is yet another approach that is based on perturbation theory, but instead of doing the interpolation the way I showed you before, we use something called Wannier orbitals. These Wannier orbitals are localized objects in real space. So there are some mathematical criteria that govern what a Wannier orbital is. And one of them is a high degree of localization. So for example, here on the right-hand side, I show a Wannier orbital that I generated a long time ago for a diamond. It has an sp3 chemical character. So you see this typical tetragonal, tetrahedron symmetry of the different bonding sites. And these Wannier orbitals can be obtained from the Bloch orbitals via a unitary transformation. It's like you have something that's delocalized in one representation, you take the Fourier transform, you get something that's localized in a different representation. So it's very much along those lines. And they're often used to study chemical bonding. And in our case, they're used for interpolation. So there's an equation here that shows you exactly how you get a Wannier orbital from a Bloch orbital via this unitary transformation. So the first part here is really just a Fourier transformation. So you can think of it as a generalized Fourier transformation, but you rotate all the Bloch orbitals with this Wannier transformation matrix. And then there is an inverse transform that is just exactly the same, but adjoint, essentially. And this Wannier transformation matrix, getting this Wannier transformation matrix is really the tricky part about Wannier orbitals, because every property of that orbital, like its position, its symmetry, the flavor, the degree of localization, it's all controlled by that U matrix. And there's lots and lots of freedom to choose the different values of this unitary matrix. But once we have such an orbital, it is now possible to perform a Wannier interpolation scheme. So I will outline it here in the example of the electronic Hamiltonian. So imagine we have a supercell, we have some Wannier orbitals sitting in that supercell, and we construct our Hamiltonian matrix in the Wannier representation. So these are Wannier functions that sit somewhere in the supercell, and we get a Wannier matrix. And what we want to get at the end of the day is the Hamiltonian in the Bloch representation in the primitive cell. So it's once again such a mapping that I showed many times before now. And of course, the Hamiltonian in the Bloch representation is really just the electron eigenvalues. So it's diagonal with the Bloch-Kohn-Sham eigenvalues here. And to go from one to the other, we can perform a Wannier interpolation. So we use the formulas from the previous slide to transform our Hamiltonian from Wannier back to Bloch. And so we first do a Fourier interpolation going from our supercell picture to the unit cell at a particular K point. So this is something you can arbitrarily choose then. And then we rotate with these U matrices. To be more precise, in practice, what you do is you do this Fourier transform and then you perform a diagonalization, because you know this matrix is supposed to be diagonal. And then you get your U matrices from that diagonalization. And this exact concept also works for matrix elements. So same picture, but slightly different. Now we deal with an atomic displacement here, but in addition, we have the same Wannier orbitals in the supercell everywhere. We construct a change of the Hamiltonian with respect to atomic displacements in the Wannier basis. And we want to get to the matrix element in the unit cell using the Bloch representation. And once again, we can do this with a Wannier transformation, a Wannier interpolation. And now we interpolate not just K, but K and Q. So both K and Q can be picked arbitrarily, which is an extremely fast process. So this interpolation, once you have obtained this matrix, is really just a global transformation, a global, let's say, generalized Fourier interpolation is very, very fast. However, the quality of this interpolation depends heavily on the quality of your Wannierization. So how you construct Wannier orbitals. Like I said, symmetry of these orbitals, localization. There's also something called the disentanglement procedure that plays a huge role. And so you have to put in some effort to get good Wannier orbitals before you can attempt this interpolation. The upshot of this is that this procedure automatically works out of the box with high-level density functionals. So that's really one of the big advantages. You can do meta-GGAs or even hybrid functionals here out of the box. I think that's all I had to say about this interpolation procedure. The remaining aspect is still how do you obtain Wannier orbitals in VASP? And we do offer various different ways to generate these U matrices. The simplest one is to just project on local orbitals. These can be atomic orbitals or hydrogen-like orbitals, something that is already localized. And when you project on these functions, you can just say, okay, this projection, when I orthogonalize it properly, is my Wannier orbital. And that gives you a lot of control over the character of these orbitals, because, for example, here I show that with this lockproj tag, you can set up 128 atom-centered orbitals that are hydrogen-like and have sp3 character. And that would be, for example, a really good fit for something like diamond, where you know the chemical nature of your bonding orbitals is sp3-like. You can also use a more automated approach that we have introduced in VASP, which is the selection of columns of the density matrix approach, or SCDM approach for short, which you can actuate via LSCDM equals true. That will find useful information in the electronic density matrix and extract this information that will give you a very localized representation of your orbitals. And you can use that to automatically find a good Wannier representation. So this is something where if you're not sure what the chemical nature of your system is, it's a really, really good starting point. It will not preserve some symmetries very nicely, but it does give you an extremely good starting point for Wannierization. And sometimes this is all you need to do. And then finally, we also offer an interface with Wannier 90, where you can use an iterative scheme to determine so-called maximally localized Wannier functions. So Wannier functions where the spread is minimized, the spread of the orbital is minimized using an iterative scheme. We offer some information on this on our VASP wiki, so there's a nice how-to page where most of these things are discussed in much more detail. And there's also a so-called disentanglement procedure. I don't have the time now to go into this. Like I said, this is really more meant as a sneak peek of a future feature that will make it into VASP very soon. But you can read up on all of this already on the wiki. Okay, so one thing that will also make it into the next release is a nice feature where we can solve a common problem with supercell-based approaches. So Wannierization, as I've just presented it, works very well in a unit cell. But if you want to use the same thing in a supercell, and mind you, we do need a supercell for our method to work, we have to jump through extra hoops. It's very expensive. The iterative scheme doesn't really work out all that well. You have issues with translational symmetry because we do need translational symmetry in order to perform our Fourier sum. So what we add is a way to transfer the Wannier orbitals from a primitive cell, where you can do all kinds of things like MLWF, SCDM before that, disentanglement, and everything works very nicely. And you can take that information and transfer it into a supercell by essentially duplicating the Wannier orbitals translationally. And in that supercell, you can then perform your electron-phonon physics. All right. And so we've done some very, very recent work. So I've done the close collaborations with people who work directly with the scan functional. It's a meta-GGA that has very good performance and can give really good phonon dispersion relations. You see that here in the example of gold oxide and nickel oxide. And in this case, we are able to use this Wannier interpolation scheme to perform also the electron-phonon interactions using the R2 scan functional. And you can see that this enhances your electron-phonon coupling here in this plot by quite some amount. There's still a lot more physics to be done here to give you any really definitive statement on what electron-phonon physics on this higher level of theory does. But this is already a nice first sneak peek. There's a preprint already available. And then the last thing I want to add is a project I've been working on for over a year now, and that is we are building an interface between VASP and EPW. So EPW, that is Electron-phonon Wannier. It is a code that performs Wannier interpolation, and it allows you access to all kinds of really high level sophisticated electron phonon physics. So that includes superconductivity, transport properties, of course also the renormalization, temperature effects, etc., etc. And the idea here is that you can use VASP as a driver to produce electron-phonon matrix elements using our techniques. So using, for example, the Wannier interpolation with higher level functionals. So you can do a scan, you can do a hybrid functional calculation. And it also takes full advantage of our projector augmented wave method. I haven't had the time to go into this detail, but it is something that is also present at the core, not just at the core of VASP, but also in the electron-phonon code. And it makes it so that our calculations are extra robust and fast. And you can take advantage of all of these features of VASP to produce electron-phonon matrix elements. And then you can use EPW to consume those electron-phonon matrix elements to perform really high-level electron-phonon physics. So this will make its appearance very soon. The manuscript is already in preparation, and is something to look forward to. Now, the summary of this final part, the sneak peek, is really just, yes, Wannier interpolation is coming. It's been in the works for a very, very long time, but we finally feel like it can be released in some form. It's very fast interpolation, but it requires a Wannier basis. So we will continue to offer more and more sophisticated ways of Wannierization, so you can also take advantage of this. It does work immediately for most density functionals. And finally, the VASP to EPW interface is something to really look forward to. So stay tuned and check out our releases. Okay, and with that, I come to the end of this presentation. I have talked about the electron self-energy and what we can gain from it from the perspective of renormalization. So the renormalization of the electronic band structure, including bandgap renormalization at both finite and zero temperature. However, there is more to it. In tomorrow's lecture, you will learn about electronic transport properties, which is also something you get. There's an ingredient you can get from the electronic self-energy, which means the lifetimes or equivalently also line widths. The code works already with spin-orbit coupling. These are things that I didn't explicitly mention, but it's something, as a feature list I want to mention here. Spin-orbit coupling is supported. We have extremely efficient parallelization schemes. You can either parallelize over bands with different memory distribution options or over K-points. It does support the aforementioned projector augmented wave method. We also support HDF5 output. So all of the information I showed you before that's written to plain text is also written to binary parsable, machine-readable HDF5. And we use our in-house tool Py4VASP to parse that information for you and give you in an easily digestible way. And I've very, very quickly brushed on this accumulator concept where you can provide certain inputs as lists of values. So for example, you can specify different values for ELF M-bands sum or for the I delta parameter, and VASP will efficiently deal with that by computing the matrix elements and then reusing them for different values for the self-energy calculations. So you can take advantage of all of this using our internal electron-phonon driver. And then there is a whole slew of things to come There is iterative Boltzmann transport. Once again, you will learn more about that tomorrow. There is the phonon self-energy. This is a huge topic again in and of itself that is also related to superconductivity. We do want to provide GPU support because we all know that's going to be the future. Wannier interpolation is here on the list. It will come out very soon. VASP plus EPW is exactly the same. And then support for higher level functionals also for the perturbative approach that I showed you before. And that is it. I thank you very much for your attention. I hope that I was able to give you a nice overview of this particular part of our new feature. It's still quite busy. There's lots of information that we keep adding to the wiki. And yeah, if you find anything that isn't quite up to par with our information online, with the tutorials, feel free to reach out. We are always working to improve these things. Thanks.
All right, brilliant. Thank you very much, Manny. That was a delightful presentation.